In this screencast, we're going to take a quick look at the Introduction to Enthalpy worksheet, but we're going to focus on manipulating thermochemical equations and stoichiometry. So the first thing we want to remember is that if you manipulate a thermochemical equation in any way, that will impact the value of enthalpy, or delta H. So remembering that enthalpy is an extensive property, if you change the amount of substance that reacts, you will change the amount of heat that you are given off or that gets absorbed. So you have to take that into consideration. So just remember, whatever you do, if it changes the amount of material, you have to take that into consideration when you're thinking about your enthalpy. A second important rule is that if you reverse a reaction, you are simply going to be flipping the sign on your delta H. Let's remember that in our potential energy diagram that we looked at before, we could look at the reaction kind of going in the forward direction, or we could read the same diagram in the reverse direction. And it doesn't matter in which direction we're reading the diagram, the delta H number is the same, but the sign is flipped. So in this particular diagram, delta H forward is exothermic because the potential energy of the products is less than the potential energy of the reactants, which means the delta H in the reverse is going to be endothermic, or positive. In these practice problems, you're just going to be looking at using some of the skills about manipulating reactions and writing thermochemical equations. Now, when you're writing a thermochemical equation, remember this is going to be a balanced equation. It's going to include all phase symbols, and it's going to include the enthalpy. And there's a couple ways we can do this. So let me do the first method first. Iron reacts with hydrochloric acid, producing hydrogen gas in a solution of iron 2 chloride. So we first start with it being balanced. One way to show our enthalpy is off to the side. We can just write delta H is negative 87.9 kilojoules, because remember, it's being released, so you want to include that as a negative delta H. A secondary method would be to embed the heat in the reaction as a reactant or product. So because in the equation, in the statement, it tells you that energy is being released, so I've got my plus sign, it means that we can simply add in our heat as a product. Now remember, we're not using a negative sign here. We're placing the heat on the product side because it's being released. If it had to have been an endothermic reaction where delta H was positive, we would have placed the energy, the heat, on the reactant side. So you need to make sure you are familiar with both of these ways of writing a thermochemical equation. For 9 and 10, we're just going to look at those manipulating rules. So if you take a look here, we have our P4 and our hydrogen making our P4H10. Here we've reversed the reaction. Everything else is the same. The amounts are the same. It's just reversed. So all we're going to do for that is reverse the sign. In 10, we're looking at hydrogen, oxygen making water. Here we have 4 times the amount. So since we went from this reaction to this reaction and we did 4 times the amount, we're going to go from here to here. We're going to do 4 times the heat. That's going to be our delta H for this reaction. Okay? So those are the 2 key rules. Now, as we move on to stoichiometry, I just want to remind everyone that you do have the PowerPoint to use as a reference. But the new big idea is that we're going to use stoichiometry to help us convert when the amount of substance changes. And the way we're going to do that is using dimensional analysis and by creating conversion factors from the balanced equation and the coefficients in the balanced equation and the enthalpy for that reaction. Because remember, this amount of energy is for these very specific amounts. So, if we wanted to think about it, 2 moles of water would be absorbing 450 kilojoules, or 2 moles of hydrogen is again 450 kilojoules, but 1 mole of oxygen is also associated with that same 450 kilojoules. So these values, these relationships are the conversion factors that we would use when we're doing dimensional analysis. Let's look at that example that's already done out for us. So notice we're starting here with the given. That will never change. From day one, when we did dimensional analysis, start with the given. Now, because in the balanced equation, the amount of energy is related to the mole amount, this is from our balanced equation, the first thing we have to do is change grams to moles. Now, notice I'm writing grams of water, moles of water. I'm labeling my substance. Please get in the habit of labeling not only the unit, but the substance that you're talking about. Because as you know, we're going to be going back and forth. We're going to be talking about different substances and different relationships. And this can be a common source of a careless error. So we start out the problem with basic stoichiometry, gram to mole conversion. And then the new thing is we're relating the energy and the moles through stoichiometry. So this is our new conversion factor, and then we're going to set this up and solve. So when I'm looking for you to work on a problem like this, I want you to be using dimensional analysis, and I want you to be showing your units and how everything lines up, and then solving, reporting your final answer to the correct number of significant figures. Now, if we think about question 11 here, it's going to be done very similar. We have the mass of the hydrogen, and from the mass of hydrogen, we have to calculate the change in enthalpy for the reaction. So we would set this up in this manner. We have the mass of hydrogen, diatomic. Before we can even think about that thermochemical relationship between energy and moles, we have to convert our mass to moles. Now, hopefully you became comfortable using the one long T-chart method when we were looking at stoichiometry earlier this year. That's really going to come in handy. If you're still feeling like you want to show this in 3 or 2 separate steps, that's fine as well. If we were to stop here, we'd be at moles of hydrogen. Now, what do we know from the balanced equation? And I oftentimes like to circle this because I want to make sure that I don't make a careless mistake. We know that for 3 moles of hydrogen, we're going to release, don't forget that negative 91.8 kilojoules. So when we solve, we're going to have accounted for the fact that even though we're doing the same reaction, in this reaction, 3 moles of hydrogen produce this much heat, if we are changing the amount of hydrogen that we are going to be using, we have to adjust for the amount of heat that will be produced. Number 12 is going to be done in a very similar manner, except here you're starting with volume and you're at STP. So again, you're given, you're going to start with this. Number 13 is a little bit different because your main given, what you're starting with, is the amount of energy that was released. So an unknown mass of iron was reacted with excess oxygen under these conditions. It was determined that this much energy was released. Calculate the mass of iron that reacted. So we're doing the same process, but we're just starting with a different given. We're going to start our T-chart with our 256 kilojoules of energy. And in the end, we have to figure out the mass of our iron. So this is where we need to focus on when iron is involved. If 4 moles of iron reacted, this would be our delta H. So another key thing that I'm just realizing I could have forgotten, it says that energy is released. We have to put that as a negative. So we put our negative 824 here. That's for 4 moles of iron. Now, at this point, if we stopped, we would be at moles of iron, but we need to get mass. So this is where we're just going to do a quick gram to mole conversion. Now, I don't have my periodic table in front of me, and I don't have my calculator, but I think this is the molar mass of iron, 55.85 grams iron. Now, here's a thing to think about. You can never have a negative mass. So see, if I would have forgotten to put that negative sign in here, and I almost forgot, and I would have done out this math, I would have ended up with a negative mass. You can't have a negative mass. So that's a sign that you just dropped some negative sign somewhere. Another thing to remember is yesterday when you were doing your work on specific heat and you were using the equation Q equals MC delta T and you had to solve for specific heat can't be negative either. It's always a positive number. So when you're solving and you see things that turn up odd, like a negative mass or a negative specific heat value, it just means you dropped a negative sign somewhere. So usually it's here in the enthalpy value, or if you're using that Q equals MC delta T equation, it's usually in the change in temperature. You forgot to make that negative. All right, good luck with the rest of these problems. I'll talk to you tomorrow.